So chemistry practical, we have paper, it is paper 3. Chemistry practical is paper 3. So, and in paper 3, there are 3 questions. You have question 1, question 2, and question 3. I hope you guys are listening. The whole questions are compulsory. So the first question is based on volumetric analysis. Can you hear me?
Yes, sir.
Okay. The second one is going to be on salt analysis, or we call it quantitative analysis. Sorry, qualitative analysis. Qualitative analysis, or they call it salt analysis. And the third part is general chemistry knowledge, or practical knowledge. General practical knowledge. Okay. So these are the 3 major aspects that you shall be tested on in your chemistry practicals. So as a result, there is a need for us to quickly look at this conception one after the other and see how best we can answer questions related to them. So we are going to start with the first aspect, which is volumetric analysis. Okay. Okay. Now this volumetric analysis is also known as, okay, we also call it quantitative analysis. Okay. And it is majorly used to detect the concentration to detect the concentration or quantitative measures other quantitative measures of a solution, right, given the concentration, given the what, the known concentration or quantitative measures of another solution. So in this case, in volumetric analysis, there are 2 quantities that are involved. One of the solutions, let's assume you have solution A, and then you have another one, solution B. Okay. Now, solution A is possibly having an unknown concentration. We don't know the concentration of this, but we know the concentration of this. This is known. So we are going to use the knowledge of volumetric analysis to detect the concentration of the unknown using that of the known concentration. Is that okay? So that's what we do majorly in volumetric analysis. So there are different forms of volumetric analysis. I hope I'm audible. So we have types of volumetric analysis. Please, can you hear me?
Yes.
So we have different types of volumetric analysis. Number 1, the commonest one is acid versus base titration. We call it acid-base titration. Okay, that's one of the commonest titration. Then you have the redox titration. We're going to call you redox titration. Redox titration is reduction oxidation titration. Okay, you have iodometric titration. You have iodometric titration. You have complexometric titration. Complexometry.
Sir, please, can you come again? My network is bad.
Okay, I said the types of volumetric analysis we have include the acid-base titration. Can you see the screen? So we have the acid-base titration, and that is the commonest. We have the redox titration, that's the reduction oxidation titration. We have the iodometric titration. We have complexometric titration, and so on and so forth. Okay, etc. Do you understand what I said? Can I proceed? Hello, can you hear me? Hello? Olamikun, are you there?
Yes, sir.
Okay, Olamikun can hear me. So I guess Emmanuel is having issues with his network. Emmanuel, can you hear me now, Emmanuel? Hello, Emmanuel.
Yes, and my network is. Yes, I can
Okay.
hear you.
Okay, I guess you're having issues with your network, right? Am I correct?
Yes, sir.
Okay. Well, nevertheless, let's just try to have the class. So hopefully, although I'm having the recorded section of this class, so maybe I will be able to compress it and send it for anything you must have missed. Okay. So that is it.
Sir, and the previous one too. Record for of the previous one.
Okay. Okay. No problem. I'll do that. So now we have the acid-base titration, which is the commonest one out of all the volumetric analysis. So the ones you might be tested on in the exam, as far as your WAEC or your GCE is concerned, you will be tested on acid-base titration, redox titration, or the iodometric titration. These are the three types of volumetric titration you could be tested on. They will not give you anything on complexometric titration. It's not for you. Okay, so mind you, you are not going to be tested on that in any way. So now, what is expected when you are dealing with acid-base titration? So that's what you want to talk about mainly today. So in acid-base titration, just like I said, one of the solutions is known and the concentration or maybe a parameter of the other one is not known. So we are going to use the value of the known concentration of the known solution to detect that of the unknown solution. So, and majorly in acid-base titration, we are going to react an acid against the base. So that's why we call it acid-base titration. So our acid most often is poured into the burette. However, we can have what we call back titration. But in most acid-base titration, your acid is in the burette. Okay. And then your base is going to be in the pipe in the conical flask. Are you listening? Okay. So, but because you are not actually dealing with the integral part of acid-base titration, like you are not doing the real titration, so I might not talk about the intricacies of all this, but just for us to have a basic understanding of the practical exercise, our basic attention is on alternative to practical questions. Note that we are going to use the burette to measure the acid, and the burette is a very long instrument like this, okay, with a key this way, and it is calibrated like this. Okay, you can see. So this is the burette. So this is where we are going to pour the acid most times for you to do the titration. And the capacity of this burette is mostly 50 cm cube. So your burette cannot take more than 50 cm cube. Okay. So it begins from 0 and ends at what, 50. It does not have more than 50 capacity. And for it is calibrated in 0.1 ml. So meaning that each of the calibration is 0.1. So you have 0.1, 0.2, 0.3, and so on and so forth. Okay, so that's where it is measured. Okay, so that is simply our, burette where we put the acid. So our base is measured using the pipette. So you are going to use the pipette to measure your base, and so it is like this, something like this. So this one is a ball pipette. It has like a rounded cylindrical size or shaped around the middle, so it's like this. So it has a dimension like this. So you have other ones that can be straight this way, and it is also calibrated like this. So it's often pipetted. So you draw the base using this instrument called the pipette, and the capacity of your pipette most often is either 25 cm cube or ml, or it can be 20 cm cube or ml. So that is what we use to measure our pipette. So after the pipette has been measured, then you drop it into the conical flask. The conical flask actually looks like this. Let me use another. Can you see that? So this is how the conical flask is. Are you listening, please? Hello? Can you get me?
Yes, sir, I can hear you.
Okay, fine. So it's about raining here. I guess that's why some network are going bad. Okay, now. So as I was saying, we need to take them one after the other. So we are starting with a simple description of how an acid and a base titration is. So we have the acid placed into this, which is our burette. Okay, and then you have the conical flask here. So this is how the titration is done. But before we begin titration, some things are very important, so we need to look at some precautions and steps that are involved. So this is where we are having our conical flask and the base. So here we have the acid, and here we have the base. Now note, what is quite important in this is that before you add the acid into the burette, some precautions are very important. So let's quickly look at precautions here. So while adding the acid into the burette, note the following. 1. So you have to rinse the burette using the acid. So that is 1. 2. So you must always ensure that before you pour the acid into the burette, you must use what we call the filter funnel. So the filter funnel must be placed on the burette to focus the acid into it. So because if you don't use it's like this, so something like this. So if you don't use the conical flask, the filter funnel, it is possible that the acid will be spilling away, so it will just pour off. So in order for you to prevent wastage, so you are going to pour the acid into the burette using a filter funnel. So, and you must ensure that there is no leakages. That's another important precaution. Okay. Then no bubbles, also no bubble formations. So what you do, you simply pour the acid into the burette until you get to a desired meniscus. It could be 0 meniscus or what have you. Okay, so that's the very first thing to do. So after you've done that, you are then going to move into the next step. So the next step here is to do the pipetting of the base. Few seconds, please. Okay, now let's look at what happens when you are trying to do the pipetting of the base. So now, what are the precautions while you are doing the pipetting of base? So as we said, you are going to use the pipette to draw the base. So when it is drawn, the following precautions has to be taken. Number 1 is that while you are doing the pipetting, you must ensure that there is no bubble formation. 2 seconds, please. No bubble formation. Right. Number 2, you must avoid what we call last drop error. What do you mean by last drop error? So while you are doing your pipetting and you have released your hand.
Sir,
Yeah.
please, I want to leave. My network is bad.
Okay.
Yeah,
Okay.
watch the.
Okay. Olamikun, can you hear me? Are you there, Olamikun?
Yes, sir. I can hear you.
Okay.
Thank you.
Okay. Good. So now, the next thing to do, what you mean by last drop error is that after you must have released your base into the conical flask, there is possibility that you have one particular drop, and that drop is yet to be released. So do not force the last drop into the conical flask. If you do that, we are going to say that is last drop error. So you avoid the last drop error. Then we also have error due to parallax. So error due to parallax means error due to what? Accurate recording, maybe measurement, when you are taking your reading. So if you don't look at it properly, for example, this is where the meniscus is supposed to be. So if you are looking at it from down or from up, it can lead to error due to parallax. So after you've done that and you have ensured that these errors are not being recorded, then you can drop it into the conical flags. So you have the conical flags here, and the base is dropped into the conical flags. So this is our conical flags. Okay, is that clear, please? Now before you begin your titration at all, you are going to add indicators. So you have addition of indicators. Indicators will be added. So this is another discussion in its own. So what are the indicators, the types, and what are the color changes for each of these indicators? Now when you are using indicator into your conical flags, you must take consideration of the colors and the type of indicators that you are using. So first, when we say indicators, we know what they are. So indicators are simply, organic acids or bases that tend to change color. That tend to change color due to a change in its pH solution or environment. So meaning that what these indicators do is that they have colors, okay, and they have the ability to change their color when they are found in different pH values. So the common indicators that we have are methyl orange. We are majorly talking about acid-base indicator here. We have methyl orange, okay. We have phenolphthalein, okay. We have methyl red, we have alizarian yellow, and so on and so forth. We have Congo red, etc. Now, but the most prominent ones that we use for acid-base titration is methyl orange and phenolphthalein. Okay, so we need to know the colors of these indicators and how they behave when they are in a base and also in an acid. Now let's assume you have a conical flask, and inside it there is what? There is a base. Okay, now you are now making use of methyl orange. Okay, now normally the color of methyl orange itself, so that's the normal color of methyl orange, is orange. Okay, now but methyl orange in acid, let's say in a base, the color will change from orange to yellow. Are we there? Okay, that is the color of methyl orange in a base. Now this same methyl orange, if it were to be in an acid, what would be the color in acid? So in an acid, the color of methyl orange is going to be pink. Sometimes they will say red, depending on the concentration of the methyl orange prepared. Okay, so it implies that if I have a base, right, and I add my methyl orange indicator into this base, the color of the base will change to yellow. So the solution in the base will now become what? Yellow. Are you getting it, please?
Yes, sir, I'm getting it.
Yeah, so that's why we say methyl orange in a base is yellow. Okay, so that's very important. Now if it were to be phenolphthalein, let's see what happens. We have conical flags here, and you have the base in here, and you are adding phenolphthalein. What happens? Normally phenolphthalein itself has a color, and the color is that phenolphthalein is colorless, so it doesn't have any color. Actually, it is colorless. So what is going to be the color of phenolphthalein when it is added in a base? Okay, so phenolphthalein is going to be pink. Okay, so that's the color of phenolphthalein in the base. Okay, in an acid, so in an acid, the color is going to be what? Colorless. So we can see this is what is happening. So the color of phenolphthalein in an acid and the color of phenolphthalein in a base. So you're supposed to be familiar with these colors and understand how it operates. Okay, so we proceed. Now we are having the burette and we have the conical flax, and we started our titration. After we have added maybe 2 to 3 drops of the indicator into the base, let's say this is the base and here is the acid. Okay, now here we have our acid and here we have the base. Now when you begin your titration, this one was yellow, it had a yellow color because we are using, let's say we are using methyl orange as indicator. So the color was originally yellow. So as you are doing the titration, what you observe is that it will get to a point whereby the yellow color will be changing to pink and it will be returning back to that pink color. So you are going to have yellow base gradually turning to pink and gets reversed. So mean that it will be turning to pink until you go back to that yellow until it gets to a point we call the equivalence point, or we call it the end point. So let me call it equivalent point because there's a difference between the two. So when you get to the equivalent point, which is theoretical, or end point, which is practical. So when you get to this point, what happens? At this point, there is going to be a color change, a permanent color change. So there is going to be a permanent color change. So for example, this yellow color will change to what? Pink at the end points. So at that point, we are going to get the slightest color change. So at that slightest color change, we are going to stop the titration. And when you stop the titration, you will then read the what? The meniscus. So let's assume when we did that, we read 16.20. So this is going to be our first titration. Are you getting my point? So it will imply that I started with a titration of 0.0 and I stopped at a titration of 16.20. So if I'm to draw the whole stuff, I'm going to have it this way. We have burette reading, okay, we have final reading, we have initial reading, then you have volume of A used. Now we can plot this like this. Now it is important to always write the units. The unit is in CMQ. Failure to put the unit, you might be penalized. So a deduction of about 2 marks. So you're going to have something like this. Okay. Now, let's assume you have something like this. So we are going to have the first titer. Write it in full. We are going to have the second titer and possibly the third titer. It can be more than 3 though. So we started with the first titration as we did here. So when we did the first titration, we started with an initial volume of acid to be 0.00. So it means our acid was originally what? 0.00. So this is 0.00. Note, the value must always be in 2 decimal places. So the final volume of acid, let's assume, was 16.20. Am I communicating? Now, can you hear me? Alamiku? You are practically the only one in class now.
I can hear you, bro.
Okay. Now, I can do the same thing for my second titration, either by filling in more of the acid again into the burette until it turns to 0, until it becomes 0, or I continue from where I stopped. So, meaning that I can say, okay, let me continue. So if I continue the second titration, this one can be 16.20. So when I run the second titration, I could possibly get 32.20. I'm just giving an example though. Then here I can then have filling it again, and then I have something like 16.20. Now if I have something like this, I can easily calculate the volume of acid used. For each of the titer, this one is going to be 16.20, this one will be 32.00, and sorry, error please. This will be 16.00, and this will be 16.20. So how do we get that? It's just final reading minus initial reading. So that will give you the volume of A used. I hope that's clear. Now, many a time when you are drawing this table, you are supposed to write the capacity of pipettes and the type of indicator that is used. So it's supposed to be written here. For example, capacity. Sorry, 2 seconds please. So the capacity of pipettes, either you are using 25 cm cube or you are using 20 cm cube, but what is commonly used is 25 cm cube or ml. So you have to write that down. You also need to write the type of indicator that is used. So what is the indicator? So if you are using methyl orange, you put it there, methyl orange. You write it in full please. So this is quite important. So the things you are supposed to note here majorly is that the values that you are actually recording must be in 2 decimal places. For example, this is 16.20, right? Not 16.2. Okay, this is 32.20, 2 decimal places. This is 0.00, not 0 or 0.0. So this is 16.20, and so on and so forth. Another thing to note again is that you must always write the unit of your burette. It is in cm cube. You can see that in cm cube. Okay, and then if you have to now do the calculation, your calculation must be only limited to those volume of A that are concordant. How do you know values that are concordant? Concordant values right? So concordant values are between plus or minus 0.2. So meaning that they will not extend out of this range. So what we mean by that is that it's going to span from 0.2, 0.1, sorry, minus 0.2, minus 0.1, 0, 0.1, and 0.2. So these are the values that you can get when you do the difference of one value of A or with the other. Okay, so for example, like the one you had 16.20, 16.00, and 16.20. These are the 3 values that we had. Now all these 3 values are concordant, because if you take the difference between 16.20 and 16.00, so you realize that the difference is what? 0.20, so which is still within this, so it is concordant. So this and this can go. if you do the same thing 16 and 16.2, you will get what? Minus 0.20, so which is also within the limit. If you do 16.2 and 16.2, you get 0.00, so which is also what? Within the limit. So this tells us that the three values here are concordant. So to get the average volume of acid used, so you are going to add the 3 and divide them by 3. So it means that the volume of acid, that is average volume now. So it's going to give you the summation of the 3, 16.20 plus 16.00 plus 16.20, everything divided by 3. Okay, so at the end you are going to get what? I guess 16.10 cm cube. So this is going to be the value of acid, or the average volume of acid used. Okay, is it clear? So that is the basics of the table and the simple titration. Now the next thing to talk about now is the formula that we often use for titration. Formula related to titration. Today we are not doing any calculation. I'm simply explaining the basics. So by next class we will talk about a lot of other questions and calculations, how they are related to titration. So the first thing is that you need to know this important formula. Number 1, mole is equal to mass over molar mass. This is the first equation, equation 1. Then the next one is molar concentration equals to mole over volume. So the unit of molar concentration is mole per dm cube. So this is equation 2. Who is that? Let me admit. Fatia. Hello Fatia. Is she there? Okay, I think she has joined. Fatia, how are you? I can't hear her responding. But she's in, so let me continue. Now, another formula that is prominent is mass concentration. So the formula for mass concentration is mass over volume. And so the unit of mass concentration is gram per dm cube. That's equation 3. Are you following? Now, there is a formula that relates molar concentration and mass concentration, and that is mass concentration is equal to molar concentration times molar mass. This is equation 4. Okay. Then the next one is the cover. CAVA over CBVB equals NA over NB. This is another one. This is equation 5. The CA there represents molar concentration of acid. And is often in mole per dm cube. Right. CB is molar concentration of base, also in mole per dm cube. Then you have our VA, that's the volume of acid. Sorry, 2 seconds please. So volume of acid in what? In cm cube. So this is often the average volume from the titration. So you have VB, so the volume of base, also in cm cube. So this one is often the capacity of your pipette. It is mostly in 25 cm cube. or what, 20 cmp. This one is average, is titer value. Okay, now then you have Na and Nb. What is Na representing? Na represents number of mole of acid from equation. So the number of mole of acid from the balance equation is Na. So Nb would be the number of mole of base from equation. So if you have an equation, for example, we can use that equation to get Na and Nb. So specifically we use this in this equation. For example, you have an acid and a base, NaOH plus H2SO4. Here is a reaction, right? So this is a base and this is an acid. A neutralization reaction leading to the formation of Na2SO4 plus H2O. So that's salt and water. Now, what is interesting about this is that we can balance the equation to get our Na and Nb. So let's balance it. 2 here, right? So 2 here. So you can see this is for the base. So it means my Nb is equal to 2 and my Na is equal to 1. So this is how to get Na and Nb from equation. Okay. No, these two Na and Nb are frequently used using the formula Ca Va over Cb Vb equals to Na over what, Nb. That's why you use this equation particularly. So this is equation, what equation do we call this? I guess equation 5, right? Yes. So, but before we leave this, there are two types of volume I need to talk about. So the volumes that you are going to encounter. So we have volume of reaction and volume of preparation. So volume of preparation and volume of reaction. So what do you mean by volume of preparation and what do you mean by volume of reaction? So when we are talking about volume of preparation, right, it is the volume that is definitely used in preparing the standard solution. Okay, so and this volume that we use in preparing are mostly between 250, let me put it that way, between 250 cm3 and what, 1000 cm3. Okay, so whenever you see a volume between 250 and 1000, it is regarded as a volume of preparation, and we mostly use this volume of preparation to calculate molar concentration and what, mass concentration. When we get there, you understand what I mean better. So whenever we are making use of volumes that are very large, like between 250 and 1000, so we are referring to what, a volume of preparation, and they are mostly used to calculate molar concentration or mass concentration. And so these two volumes have to be converted. Volume of preparation always need to be converted to DMP. So, and if you need to convert them to DMP, what do you have to do? You divide by 1000. Conversion, right? So that will be divided by 1000. Okay, for example, if you have 250 cm3, it's equivalent to 0.25 DMP. Okay, if you have something like 500 cm3, it's equivalent to 0.5 DMP. So whenever you have values in cm3 and it is the volume of preparation, so you can convert them to DMP. That's very, very important. Okay, now we also have volume of reaction. Now volume of reaction are majorly used to estimate or calculate. Okay, let me say they are often used in the CAVA, and then also maybe to calculate some other quantitative, measures. So whenever you are talking about volume of reaction, they are always limited between 20, let me say around 20. They may be smaller than that though sometimes. So okay, let me use 10, between 10 to 100. I've taken a very large value now. Expand. So many a time the volume of reaction do not transcend this. Okay, for example, when you look at VA, that is the capacity of your burette. Okay, so it is 50, so it does not transcend 50. So the tighter value of the acid is always between 10 to 50. You get it? So you can be having something like 25.0, 27, right? So it will not exceed what, 50. Okay, but VB2 is either 25 or what, 20, and they can be within this range of values. You can have 10, you can have 12, you can have 15, and so on and so forth. But note that these values are very small. They are smaller when you compare them to the volume of preparation. So and they are mostly used in the CAVA calculation, except when otherwise stated. Okay, and you are going to see questions related to that. So another formula that is quite prevalent is C1V1 equals what, C2V2. Sometimes they write it as C initial V initial equals to C final V final. So this is equation 6, if I'm not mistaken. So Ci here represents initial concentration of solution. 2 seconds. So this is initial concentration of solution. Okay. Then Vi represents what? Initial volume of solution. Cf represents final volume, final concentration, sorry, of solution. While Vf represents final volume of solution. Is that clear? So CIVI equals to CFVF. Now, so for example, you have a solution, right, with an initial concentration. Let's assume the initial concentration was 0.5 mole per dm3. Okay, so and the volume between this point and this point was just 10 cm3. Okay, so it means that my initial concentration C1 was 0.5 mole per dm3. Okay, and my V1 is 10 cm3. So now if I added water, and I increased the volume, and the volume became 50 cm3, so definitely the concentration will change. So let's assume that now the final volume Vf is 50 cm3. So what is now going to be the the final concentration? That's Cf. So with this, we can make use of the formula we have just stated. So that will give us what? Let's do that here quickly. Few seconds, please. Now, we are going to have C1V1 equals C2V2, or UCIVI equals to CFVF. So C1 is 0.5 multiplied by V1 10 is equal to C2, which we are looking for, and V2 is 50. So you can do that, divide both sides by 50 and 50. So this and this is gone. This is gone here. This one is gone here. So this will give us C2 is equal to 0.5 divided by 5. So how do we do this? Let's multiply both by 2 times 2. So this will give us 1 over 10. So that will give us 0.1. So the answer to this is 0.1. C2 equals to 0.1 mole per dm cube. We also have the formula percentage purity. So percentage purity equals to mass of pure over mass of impure times 100. So this is equation 7. You have percentage impurity is equal to mass of impurity over mass of impure times 100. This is equation 8. So we also have number of particles. Now here it could be number of atoms, ions, or molecules. So this is equal to mole times Avogadro's constant. Avogadro's constant is 6.02 times 10 raised to the power of 23. So this is equation 9. This is the ninth equation.